Hey friends, welcome to my video on how to calculate the battery load profile. Before we understand how to estimate the battery load profile, let us have a quick recap of a typical industrial power distribution system. In a typical industrial power distribution system, normal power supply is provided through grid power or a captive power plant. This power supply takes care of all the loads that run under normal operating conditions, including essential loads and vital loads. Duplication of power supply sources normally provided to improve reliability and to permit regular maintenance. In case of failure of mains power, the essential loads or the emergency loads and the vital loads are supplied through an emergency diesel generator. Some examples of these loads are emergency lighting, key process loads, fire and safety systems, etc. In the event of failure of the emergency power, the critical or the vital loads are supplied through a AC or DC UPS system. Some examples of these loads are safety critical shutdown system, escape lighting, telecom systems, etc. Failure of the DC UPS power can result in fault detection devices unable to detect faults, breakers unable to trip on faults, local and remote indication to become inoperable, etc. Whereas failure of the AC UPS power will lead to total loss of power to the plant safety systems and will render the plant unsafe for further operation. So what is a UPS or an uninterruptible power supply? A UPS is an electrical apparatus that provides critical power to a load or loads when the input power source or the mains power fails. A UPS is typically used to protect hardware such as computers, data centers, telecommunication equipment, or other electrical equipment where an unexpected electrical power disruption could cause injuries, fatalities, serious business disruption, or data loss. In a UPS, the energy is generally stored in batteries. UPS have the advantage of immediate protection against input power interruptions. UPS units range in size from ones designed to protect a single computer to large units powering entire data centers or buildings. The world's largest UPS, the 46 megawatt battery energy storage system in Fairbanks, Alaska, powers the entire city and nearby rural communities during power outages. Let us now understand the steps for building up a battery load profile. The first step is to gather the project loads into a load profile. IEEE 485 classifies individual DC loads as continuous, not continuous, and momentary. Continuous loads are those which are energized throughout the duty cycle. These loads include lighting, continuously energized coils, power to protective relays, FNG systems, communication systems, etc. Non-continuous loads are those which are energized only during a defined portion of the duty cycle. These loads may switch on any time within the duty cycle and may be on for a set length of time. They can be removed automatically or by operator action or continue to the end of the duty cycle. These loads include critical ventilation system loads, valve actuators, etc. Whereas momentary loads are short duration loads not exceeding 1 minute at any occurrence. These loads include inrush currents, circuit breaker operations, valve operations, isolating switch operations, motor starting in rust, etc. For nickel cadmium batteries, even if the load lasts for less than 1 second, it is considered to last for a full 1 second in line with IEEE 1115. For lead acid batteries, even though the load may last for only a few cycles, it is considered to last 1 full minute in line with IEEE 485. Loads that occur at a random should be shown at the most critical time of the duty cycle in order to simulate the worst case load on the battery. Once the continuous load, the non-continuous load, and momentary load of a project has been estimated, combining all these three loads together gives us the battery load profile for that project. Another important factor of a battery load cycle is a battery duty cycle duration or the battery autonomy. Battery autonomy is a measure of the time for which the battery will support the critical loads during a mains failure. Battery autonomy is a function of the battery charge state, its capacity, and the load size. Battery autonomy time can be decided based on various factors. It is the estimated time that may be required to replace a faulty charger. Once failure of mains and emergency power happens, then the battery system is required to supply critical loads. Hence, the battery autonomy can be decided based on the total time required for the plant to be shut down safely and the personnel evacuated safely from the plant. Most clients specify the battery autonomy time required for their onshore and offshore installations. Sizing a battery is science, and there are various standards which dictate the exact steps to be followed for sizing of a battery. IEEE 1115 provides the recommended practice for sizing of nickel cadmium batteries. IEEE 485 provides the recommended practice for sizing large lead acid batteries, whereas IEEE 1189 provides the recommended practice for selection of valve regulated lead acid batteries. However, building a battery load profile is like art. Generation of a proper load profile is critical to the outcome. We should develop the load profile using the worst case and determine the sequence of the loads. Not knowing the sequence of the loads will lead to conservatism. Conservatism will unnecessarily increase the required battery capacity, which will result in a costly battery. Let us now work out an example of a battery load cycle. For our example, let us consider that we have to size a 110 volt DC battery to supply the DC loads of a 11 kV switchboard. The battery autonomy time is considered as 4 hours. Number of breakers in our example is 15 numbers, and the DC loads of the switchboard are as given in the table below. Protection relay, 1 number. This is a continuous load and the load is 18 watt. Similarly, there are other loads as indication lamps, multifunction meter, trip circuit supervision relay, spring charging motor, lockout relay, trip coil, closing coil, emergency lighting of the switchgear room where the 11 kV switchboard is located. Quantity of these loads in the switchboard is as given in the table, and the type of load, whether the load is continuous, momentary or non-continuous, is indicated in the table along with the wattage of each load. Let us also consider the sequence of operation of the breakers as below for estimating the battery load cycle. We will consider tripping of all breakers simultaneously at the start of the cycle. Thereafter, simultaneous spring charging of all the breakers, followed by closing of all breakers simultaneously, and then tripping of all breakers simultaneously at the end of the cycle. Please note that the sequence indicated here is just for explaining the battery load profile. In a practical case, engineers will not close all the breakers immediately after a trip without identifying the cause of all breakers to trip simultaneously. We can now calculate the loads on the battery bank as below. Load during tripping of the breakers will be the trip coil load plus the burden of all the lockout relays. This is a momentary load, and the total load during tripping of the breakers in our example works out as 7500 watt. So amps during the tripping works out as 68 amps. We can similarly calculate the DC loads for closing operation and spring charging condition. Duration of the loads during tripping, closing or spring charging operation shall be as given in the table, and these data can be obtained from the data sheet of the 11 kV switchboard. Continuous load on the battery bank can be calculated by adding up all the continuous loads like protection relay, indication lamps, multifunction meter, trip circuit supervision relay, etc. This load works out as approximate 4 amps, and the duration of the continuous load in our example will be approximately 4 hours. While the load for emergency lighting works out as 11 amps, and the duration of this load is 90 minutes. Once the individual loads have been calculated, we can compile these loads in a graphical form as per the sequence of operation discussed earlier. We can also tabulate the loads to depict the total load at any given instant in a battery load cycle. The battery load cycle is divided into various periods, where period is the portion of the load cycle with constant load. For momentary loads, 1 second shall be the minimum duration for nickel cadmium batteries, while for the lead acid batteries, duration of momentary load is kept as 1 minute. Spring charging motor inrush has been ignored to keep the example simple. With this, now our battery load cycle is complete and ready for use. This concludes my video on how to estimate a battery load profile. Thanks for watching. I hope you enjoyed this video. If you would like to see more such videos on electrical topics, please subscribe to my channel